Hey everyone, welcome back to Daily LeetCode channel. Today we're diving into an elegant and surprisingly tricky LeetCode problem, 2141, maximum running time of n computers. Imagine this scenario. You have n computers and a list of batteries, each with a fixed number of minutes it can run. You can freely swap batteries in and out instantly, and your goal is simple. Keep all computers running simultaneously for as long as possible. But here's the twist. None of the batteries can be recharged, and each computer can hold only one battery at a time. You're allowed unlimited battery swapping, but once all total power is consumed, the system shuts down. So the challenge becomes, what is the maximum number of minutes we can keep every computer running at the same time using optimal battery management? In today's video, we'll break down the intuition behind the problem, walk through the example provided, and then build the optimal solution using binary search and some smart resource distribution logic. If you're preparing for interviews, this is a great problem to test your understanding of allocation strategies and binary decision-making. Let's get started. Now let's take a look at example 2 to better understand how this problem works. We're given n equals 2 computers, and the batteries are 1, 1, 1, 1. Each battery can only run a computer for 1 minute, but we have 4 of them available. To start, we insert battery 0 into the first computer and battery 2 into the second computer. Both computers will run for 1 minute before those batteries are completely drained. At that point, we immediately swap in the remaining batteries. Battery 1 goes into the first computer, and battery 3 goes into the second computer. Since swapping takes no time, both computers resume running without any delay. After the second minute, these final 2 batteries are also drained. At this point, we have used all 4 batteries, and there is no remaining power to keep either computer running. So, the maximum amount of time we can keep both computers running simultaneously is 2 minutes. That's why the output for this example is 2. This example highlights the core idea of the problem. You're not restricted by the battery to computer assignment at the beginning. Instead, you're limited only by the total combined battery life and how well it can be distributed across all computers. We'll walk through a neat and compact Python solution for LeetCode 2141, maximum running time of n computers. I'll read each line of the code, explain what it does, and connect it back to the problem statement so you can see why the approach works. Line 1. Class solution. This just defines the class required by LeetCode. Nothing special. It's the usual wrapper for the solution method. Line 2. Def max runtime. Self int array list int. This declares the function with 2 inputs, n, the number of computers, and array, the list of battery runtimes. The function will return an integer, the maximum number of minutes all n computers can run together. Line 3. Array sort. Sort the battery list in non-decreasing order. Why sort? Later we'll repeatedly look at the largest battery, array -1, and decide whether it's too big relative to what we can sustain per computer. Sorting lets us easily access and remove the largest batteries from the end. Line 4. Total equals sum array. Compute the total available battery minutes across all batteries. This is the total resource pool we can distribute among the computers. The final runtime cannot exceed total/n for a simple reason. If you divide total minutes evenly across n computers, that quotient is an upper bound on how many minutes all n could possibly run simultaneously. Line 5, start of loop. While array -1 greater than total/n. This is the key insight expressed in code. Total/n is the current even share candidate runtime per computer. If the largest remaining battery, array -1, is greater than this even share, that battery cannot increase the runtime beyond the even share. Instead, it can be thought of as a dedicated resource that could support its own computer beyond the average. Practically, if a single battery is larger than the average, we treat that battery as assigned to a single computer and reduce the problem to fewer computers and fewer batteries. So while the largest battery is strictly larger than the current even share, we remove it from consideration and decrease n accordingly. Line 6, n-1. Since that largest battery will be treated as a separate allocation, it alone can serve one computer for a long time. Decrement n. The number of computers we still need to support with the remaining batteries. Line 7. Total -1, array pop. Remove the largest battery from the list and subtract its minutes from total. Array pop removes and returns the last element, the largest, because we sorted. We also removed one computer from the group to be evenly supported, so we also removed that battery's minutes from the pool. Loop explained with intuition. Think of the algorithm as compute the fair share total /n. If a battery is bigger than that fair share, it can be locked to run a single computer longer. But that reduces how many computers remain to be balanced by the rest of the batteries. Repeat, recompute the fair share with fewer computers and the remaining batteries. Continue until the largest remaining battery is not bigger than the fair share. Line 8, return total /n. Once the loop finishes, every remaining battery is at most total /n, n in size. That means the remaining batteries together can be redistributed, so all remaining n computers run for total /n minutes. Integer floor division is correct here, because runtime must be an integer number of minutes. So we return the even share total /n as the maximum possible minutes all n computers can run simultaneously. Complexity. Sorting takes O(m) log m, where n is the number of batteries. The while loop pops at most m elements, and each pop is O1, so overall complexity is O(m) log m. Space usage is O1 extra beyond input. We modify array in place. All right, let's go ahead and hit the Run button to validate our solution with the sample test cases. And there we go. All the provided test cases have passed successfully. The logic is holding up exactly as expected. Now, let's submit the solution to check it against the full set of hidden edge cases. Submission complete, and it's accepted. All edge cases passed as well. This confirms that our greedy even distribution approach is both correct and optimal for the problem. That wraps up today's walkthrough of LeetCode problem 2141, maximum running time of n computers. We explored the problem in depth, understood the reasoning behind the greedy reduction approach, and verified that the solution passes every test case, including all hidden edge cases. If you found this helpful, feel free to check out the other problem explanations on this channel. I post clear, intuition-driven breakdowns just like this one to help you build confidence for coding interviews. Thanks for watching, and I'll see you in the next video.